Everyone. So in this video we are discussing 2022 past year of BBE course, and the paper is Basic Econometrics. We have already discussed for 2023. So you are supposed to attempt only 5 questions. You will be given a total of 8 questions in the exam. Okay. Now starting with the first question. Comment whether the following statements are true or false. Give reason or explanation in 2 or 3 sentences. So the first statement is, if all the assumptions of a regression model are satisfied, then its estimators are blue. We know the estimators are best linear unbiased estimator when there is no multicollinearity, no autocorrelation, no heteroscedasticity. So this statement is true, and it won't be blue when either of them is present. Okay. Now moving on to the B part. Expected value of an error term may be either positive or negative, but never zero. We know it is one of the assumption of the OLS estimator that expected UI given the values of xi is 0. So this statement is definitely false, because it is expected that the average of the error terms turns out to be 0. Okay. Now these are fairly simple questions. C part. In ordinary least squares, this might be a misprint. The attempt is to minimize the sum of residuals. So if you have thoroughly done it when you were supposed to find the normal equations, our goal is to minimize summation ui hat square, not summation ui hat. So these are the sum of the residuals, but this is sum of the square of the residuals. So we are supposed to minimize sum of the square of the residuals. So this statement is false. Now D statement. In order to avoid dummy variable trap, number of dummies should be equal to the number of categories of a qualitative variable. This statement can be true, but there is a condition when there is no intercept. So suppose if we have m categories, so either we can introduce m dummies, or what we can do is we can introduce m minus 1 dummies and then plus intercept. So we have two ways to overcome the dummy variable trap. First is introducing m dummies without intercept, or introducing only m minus 1 dummies but with an intercept. So it would be better if you mention this condition as well. So this would give an impression that you know the answer pretty well. Okay. Now coming to the E part. Slope of a linear model will become its elasticity if model is transformed to double log model. So a double log model is of the form, starting from the basic linear model. First thing is you should know the difference between linear in parameters and linear in variables. So OLS model is linear in parameters, not in variables. Okay, I hope this is clear. Now initially our model is y equals to beta naught plus beta 1 x. Now the interpretation of beta 1 would be, if x increases by 1 unit, what would be the change in, by how much unit would y increase or decrease? What would be the change in y? Now if you're transforming into a log model, log y equals to beta naught plus beta 1 log x, 1 by y dy on differentiating will get equals to beta 1 by x dx. So this term gives the percentage change in x, and this term gives the percentage change in y. So beta 1 gives percentage change in y upon percentage change in x, which is nothing but elasticity. Okay, so it will become the elasticity. So this statement is true. Now moving on to the F part. Heteroscedasticity is quite common in the time series data. So we know heteroscedasticity is present in case of cross-sectional data, and when we talk about multicollinearity, it is present in time series data. Also, autocorrelation can be present in time series data. So heteroscedasticity, so in this case you can define what heteroscedasticity is, and in depth you can tell that it is present in not time series but cross sectional data. So this statement is false. Now G part, multicollinearity exists when the error term is correlated with the independent variable. So this is a false statement. Multicollinearity exists when there is a linear relationship between the independent variables. So if there is a linear relationship between the independent variables, we have a case of multicollinearity. It is nothing related to the error term. Okay, so this statement is false. Now looking at the last statement, adjusted R square value is always positive in a regression model. We know R square lies between 0 to 1. And adjusted R square, the formula of adjusted R square is 1 minus R square into n minus 1 upon n minus k, where k is the number of parameters that are included in the model. So adjusted R square takes into consideration it is like a penalty which is being imposed, taking into consideration the degrees of freedom. Now suppose R square is 0. If R square is 0, R bar square becomes 1 minus n minus 1 upon n minus k. And if k is greater than 2 or greater than 1, greater than equal to 2, then R bar square can be negative. So this statement is false. You need to remember this formula. This would be helpful in the next few questions as well. Okay, so we are done with this. We'll move on to the second question. Just have a look at what the second question is asking. So the question is saying that there is a relation between sales and advertising expenditure of a sample of 20 firms. So this is a model where sales is dependent on the advertising expenditure, and as expected the value is positive. So if the advertising expenditure increases, the sales would increase. Now since the R square of the value of the model was low, so it is coming out to be low, it was decided to add a new variable. Okay, now they have added a new variable to the model, x2i something, which is the, okay, which of the two models is better? How will you test whether the new variable x2 should be added or not? So you should remember one thing, a new variable should be added to the model when mod of t is greater than 1. Since we know the coefficient of the new variable, but we don't know the standard error, so we cannot use this, but mod of t greater than 1 results in R bar square increasing. So if adjusted R square increases, then only it makes sense to add that particular variable into the model. Now you must be facing the issue about how we are supposed to find adjusted R square. So in this case, the formula of adjusted R square is 1 minus R square n minus 1 by n minus k. So you need to remember this. They have asked two questions from this. So in the model 1, for model 1, adjusted R bar square for model 1 is 1 minus 0.424 into n was 20, n minus 1 would be 19, and the first model k is 2, so 18. So I'll just solve it as well. 1 minus 0.424 into 19 equals to divided by 8 equals to. So this is coming out to be 0.392. So this is r bar square 1. Now similarly, using the same formula, we can check for r bar square 2. R bar square 2 would be 1 minus r square into n minus 1 upon n minus k. So this is nothing but 1 minus 0.53, n minus 1 would be 19, n minus k would be 17. So what we have is 1 minus 0.53 into 19 divided by 17. So adjusted r bar square in this case is coming out to be 0.474. So since adjusted r bar square, look at the one in the green values, this was for the first model and this is for the second model, and since adjusted r bar square has increased, so it makes sense to use the second model. So the second model would be better. I hope this is clear. Okay, now next question, how will you test the equality of two regression coefficients in a multiple linear regression model? So suppose if we have a model like y equals to beta naught plus beta 1 x1 plus beta 2 x2. Now if we want to check whether beta 1 equals to beta 2 or not, so our null hypothesis should be beta 1 minus beta 2 should be equals to 0. Because if we do not reject this null, so this would mean beta 1 is equals to beta 2 only. And our alternative should be beta 1 minus beta 2 is not equals to 0. So this would mean beta 1 can be greater than beta 2 or beta 1 can be less than beta 2. Both are possible. So this is a two-tail test. Okay, I hope this is clear. Now we'll move on to the third question. Sorry. How would you interpret D of the Durbin-Watson formula used to detect autocorrelation? So we know, okay, let's read the question first. Show the necessary steps which are employed to obtain rho from D. Is there any relation between the two? What are the assumptions underlying the use of Durbin-Watson statistic? So it is highly expected that they would ask you a question on this. So the formula of Durbin-Watson statistic is summation ut hat minus ut minus 1 hat square upon summation ut hat square. And since it is taking a lag, so this would range from t equals to 2 to n, and I should write in a proper space. Okay, so the Durbin-Watson is summation ut hat minus ut minus 1 hat का whole square upon t equals to 2 to n upon summation ut hat square t equals to 1 to n. So this is the Durbin-Watson statistic which is being asked in the question. Now ut, we assume ut follows ut minus 1 plus et, which is this is the white noise error term. This won't be relevant for you. So with the help of this, we can find the value of rho. And how do we interpret the Durbin-Watson test? So this is the relation between Durbin-Watson test and rho. And rho lies between minus 1 to 1. So D would lie between. So if rho is minus 1, so this D would become 2 times 1 minus of minus 1. So 2 times 2, so it's 4. D would become 4. So rho equals to minus 1, if rho equals to minus 1, d equals to 4. So this would mean we have dl du 4 minus du 4 minus dl. This, so now we had when rho equals to minus 1, d equals coming out to be 4. So this is closer to 4. So here this is a case of negative autocorrelation, because since rho is minus 1 and rho gives you the value of the correlation, and if rho is 1, d would be 2 times 1 minus 1 is 0. So this is a case of positive correlation. And this is a indecisive zone. You cannot say anything about this. This is also similarly an indecisive zone. And between these two values, what we have is we do not reject the null hypothesis that there is no autocorrelation. So this would mean there is no autocorrelation. Okay, now talking about some of the assumptions which are being used when we go for a Durbin-Watson test. First is there should be an intercept term present in the model. Intercept term should be present. And then there it is about first order autoregressive scheme for the error term, that is ut equals to rho ut minus 1 plus epsilon t. We are not using rho ut equals to rho ut minus 1 plus rho square ut minus 2. So we are confining it to t minus 1 only. Okay. And the third, one of the more important assumption is that ut follows the normal distribution. This is the third assumption. The fourth assumption is there is no lagged value of the dependent variable. I'll show what that means. It means, suppose we have a model y t equals to alpha naught plus beta 1x plus x1 plus beta 2 x2 plus beta 3 y t minus 1. So this is the lagged value of the dependent variable. So if you have a model like this, we cannot use the Durbin-Watson test. Okay, I hope this is clear. Okay, so we are done with this. Now looking at part B. What is multicollinearity? So multicollinearity is a linear relationship between two independent variables. Okay, multicollinearity is a linear relationship between two independent variables. What is its impact on the regression coefficients? So we know when multicollinearity is present, the estimators are not blue because the variance is very high, so they are inefficient. Okay. Now explain how you can reduce the multicollinearity in a model by transforming the variables in a model. So transforming, we have two methods. First is first order difference. And the next one is ratio difference, ratio transformation. So if two variables, first order is you subtract it from, so first order is, suppose you have observations for n time period. So you subtract every observations from, so suppose if you're talking about tth observation, you'll subtract t minus first observation. So it is expected that the difference form would not be would not have multicollinearity. Second is ratio. Suppose we know that x2 is somewhat alpha times x. Okay, suppose x2 is alpha times x3, then we can use a ratio like x2 upon alpha x3 to check. So the ratio transformation would automatically make sure that this problem of multicollinearity is being reduced. I'll give you an example. Suppose GDP is dependent on population. So suppose if you're talking about some other factor, suppose income of a country or the prosperity of a country. This is dependent on GDP, then population, and it is expected that gross domestic product, we are not talking about per capita, this would be dependent on population as well. But if we introduce a new variable, which is GDP upon population, so then in that case, this would not be collinear with some other variable. So the problem of multicollinearity can be solved in this case. Okay. Now, looking at the C part, I'll just erase this. Okay, now looking at the C part, show how does the slope, intercept and R square of a model undergo a change after both the dependent and independent variables are scaled by the researcher to simplify the calculation. So suppose we say W1 into Y1, and similarly xi values are multiplied with a weight W2 and yi values are multiplied with the weight W1. So if we have a model like this, yi equals to beta naught plus beta 1 x1 plus beta 2 x2. Okay, we are talking about, okay, let's confine it to one variable only. So suppose we have beta 1 plus beta 2 x1 xi. Now we know the value of beta 2 is, beta 1 is summation xi. Okay, if you want to, this is the value of summation beta 2, summation xi yi by summation xi square. Now if we want to find the value of beta 2 star, we have the value of beta 2 hat, this should be summation xi star yi star upon summation xi star square. So xi is nothing but w2 into xi, so we would have w2 outside, and corresponding to yi star we would have w1. So this would become xi star xi into yi upon, from summation xi star, the weight of xi star is w2, so w2 square would come out into summation xi square. So this would be w1 by w2 into beta 2 hat. Similarly, we can solve for beta 1 hat star as well, which is nothing but y hat star minus beta 2 hat star x bar star. So if you put the values, you'll get beta 1 hat star equals to w1 into beta 1 hat. w1 was the weight assigned to yi. And one of the important properties is R square would remain same. So if you're transforming the dependent and the independent variables both, it won't impact the R square. Okay, now moving to the next question. Question 4. Data was collected of 98 schools. So we have n equals to 98. The researcher tried to run a regression of the cost structure of schools as a function of number of students. So cost is dependent on number of students studying in the school. In addition, the school differs on account of their nature. So it depends on the nature of the school as well. That is, some of these schools are special schools imparting education to students with special needs. So there are two types of school. First are normal schools and then special schools. Rest being general schools. Okay, normal nahi general, which is the same thing only. Also, some of the schools are located in cities. Now, it is a function of number of students. The other thing is it depends on the nature of the school, and the thing is its location, whether it is in city or city or far from it. Okay. Now what they're asking is they're asking to develop a regression model where cost structure of a school is a function of the number of students studying in that school. The model should incorporate dummy variables accounting for nature of school and location. Okay. So now suppose if we have a dummy variable d1 for nature, d2 for location, we can have d1 equals to 1 for special school and 0 for normal. d2 equals to 1 for the school in the city, 0 if it is far away. You can define d1 and d2 in any form you want. Now what they are asking is, okay, so the cost would dependent on alpha naught plus beta 1 into n, where n is the number of students, plus beta 2 d1 plus beta 3 d2, right? And it could take this form as well, beta 4 d1 d2, which would mean a special school which is in city. This intercept would mean this value, beta 4 would give the impact of the cost when we are talking about a special school when d1 is 1 and it is in city. Okay. Now write down the regression equation clearly bringing out the difference between special and general schools and between schools located in a city and located far from it. So if we are talking about, so we can infer 4 things from it. Suppose we are talking about so if we're talking about cost of a school, special school and located in city, so this would be alpha naught plus beta 1 n. Now it is a special school, so d1 would take value 1, so this would be beta 2. In the city, so it would be plus beta 3 and beta 4 because it is both. Okay, now clearly bringing out the difference between special and general schools and between schools located in city and far away. So you can put the values according to what the demand of the question is. So if it is in city, d2 will take value 1. So if I want to find the cost of a normal school which is far away, so normal school is taking value 0 and far away is taking value 0. So for a normal school, the cost would be, this would be 0, this would be 0, this would be 0. So for a normal school which is far away, the cost would be alpha naught plus beta 1 n. Similarly, you can interpret the other results as well. Now, how would you test whether nature of school impacts the cost structure? Now, if you want to know whether the nature of the school impacts the cost structure or not, now look at this coefficient. I'll mark this in green. If d1 equals to 1, this is when the school is special. So if the beta 2 is greater than 0 and its t value is coming out to be greater than 1, that is, if the coefficient of d1, which is beta 2, is coming out to be statistically significant and greater than 0, this would mean the cost of a special school would be higher, right? And if this coefficient is also coming out to be significant, so it would mean the cost of a special school which is located in the city, because d2 is taking value 1 and d1 is taking value 1. So this is a special school which is located in city. The cost is higher by beta 4. So this would help us in knowing about the impact. Is this clear? Okay, this is a monologue only. I thought this is an active live class. Okay. Now moving to the next part of the question. So it would be expected that a school in city would be more costly, and a school which is for the special needs would be more costly, because they need to have specific amenities and this should be accessible to all, so they need to take care of certain health requirements as well. So accordingly the coefficient would take the signs. Okay, now moving on to the B part. A business economics student was interested in running a regression between the stock price and time period measured in months. So stock prices is alpha naught plus beta 1 t. Suppose it is a function of time period. Sorry, because of COVID-19 impact on stock prices, he decides to run two separate regression. First for period while second for period this. So he's running two different regressions depending on the time period. Jan 2010 till December 2019, then Jan 1 2020 till December 2021. What is the econometric problem he was trying to address by constructing two regression equations? So it might be the case that beta 1 and alpha, the slope and the intercept value would be different for these two time periods. So this is a case of a structural change, because it impacted the economy in such a manner that it is expected that the link between the time period and the stock prices might have changed. Okay, so that's why he's trying to have two different regression equations so that it can incorporate both these things. Now someone suggested him to run only one regression incorporating features of both equations. Do you think the suggestion was correct? If yes, then develop such an equation. If no, then identify the mistake in the suggestion. Now what he can do is, so suppose the model is SP equals to alpha naught plus beta 1 t we already had, and now he can introduce a model alpha 1 alpha 1 dt plus beta 2 dt and then t, capital T, this time period. So he can create a dummy variable for which the value is 1 for this time period and 0 for this time period. So if it in this model he's able to incorporate both the time periods. So if we're talking about the first time period, so the value of the model would be alpha naught plus alpha 1 plus beta 1 plus beta 2 into t. So the slope coefficient has changed and the intercept coefficient has also changed, and then the person can check the significance of alpha 1 and beta 2. So by checking the significance of alpha 1 and beta 2, you will get to know whether there is any structural change in the slope and in the coefficient of the intercept as well. Okay, I hope. So now moving to the fifth question. A researcher fitted the following model for 64 employees where wages in rupees was regressed on experience in years. So wages is dependent on experience and then on age, and age of employees in years. These are the following results. We are supposed to interpret the two partial slope coefficients. So this would mean if experience increases by 1 year, so experience in year, so if experience increases by 1 year, it is expected the wage would increase by 0.325 into 1000 rupees. So this would be, so if experience increases by 1 year, wage increases by 325 rupees. Similarly, if the age of the employee increases by 1 year, the wage would fall by 0.003 into 1000 rupees. So by rupees 3, wage would fall by rupees 3 as the age of the employee increases. Now test whether experience and age are significant variables. So the standard error is given to us. For experience, the t value would be 0.325 by 0.032, which is greater than 10, so it is significant. Similarly, for age, the t value would be 0.00073, which is also coming out to be a very high value, so this would be significant as well. So both of them are coming out to be significant. Now the next part of the question they are asking, the next part they are asking, is the model overall significant? So to find the overall significant, we use F test. So the formula for the F test is k minus 1 upon 1 minus r square n minus k. Here r square is 0.667, k is 1, 2, 3. 3 minus 1, 2. So since there are 3 parameters in the model, so k is 3 and 1 minus r square would be 1 minus 0.667. So this is giving us a value of 0.333. Divided by n minus k, 64 minus 3, 61. So we have the value. Okay, you can use the calculator because it is already mentioned that you are allowed to use it. So if you find it, the F value is coming out to be 61, which is very high value. So the model is statistically significant. How will you calculate adjusted R square? So this is another question that you can see from adjusted R square coming out. So adjusted R square is 1 minus r square n minus 1 upon n minus k. You can put this values. R square is 0.667. N minus 1 would be 63. N minus k is 61. So it is 1 minus 0.333 into 63 upon 61. So the final value would be 0.333 into 63 equals to divided by 61. So adjusted R bar square is coming out to be 0.656. And you can see this is coming out to be less than R square, which is always true. Okay. Now, looking at the next part of the question, what will be the wage of the employee who has an experience of 11 years and whose age is 50 years? So we just need to put the experience here and the age 50 here. So it would be 20 plus 0.325 into 11 minus 0.003 into 50. So this is coming out to be 23.425 into 1000. So 1, 2, 3. So it would be 23425. So for an employee who has an experience of 11 years and whose age is 50 years, his expected income is 23,000 rupees, 23,425. Is this clear? I'll repeat it once again. So if we are talking about an employee who has an experience of close to 11 years, so we'll put 11 in the experience, and whose age is 50 years. So if he's 50 years old, we'll put 50 here and we'll solve this equation. We are finally getting this value. So this would mean, on an average, if an employee has 11 years of experience and whose age is 50, it is expected that he would be earning around rupees 23,425. Okay. Now moving on to the last part. Why do you think the sign of the variable age is negative? So you need to give the economic interpretation of it. So it is expected that as your age increases, your wage is falling. This might be due to the case that the productivity level as the age increases actually falls, because the young population has more capacity to do work. So the employers won't prefer a older workforce. Okay, now moving to the sixth question. Okay, in a multiple regression model, The coefficient of the explanatory variable is the partial slope coefficient and measures the change in the dependent variable due to a unit change in the explanatory variable. I hope you know the meaning of partial slope coefficient. Keeping the impact of all other explanatory variables considered in the model constant. Explain how is the impact of all other variables kept constant. Okay, I'll give you an example. Suppose we are talking about demand for a good and it is alpha naught plus beta 1 price. Okay, beta 1 income, price would also be a factor, plus beta 2 wealth. So if we know, it is expected that wealth and income would be highly correlated to each other. So what we'll do is, firstly, we will have this regression. We will regress demand on A naught plus B naught wealth. First we are regressing it on wealth plus U1. So on this base, with the help of this, we will get U1 hat. Now in the second case, we will regress income on wealth. So suppose alpha we have already taken. Okay, C naught plus D naught times wealth. So plus U2. If we regress this, we will get U2 hat. Now if we regress U1 hat on U2 hat, so suppose we are getting H naught is the coefficient into U2 hat. So this H naught would give us the impact of the income solely. Okay, I'll try to explain it with the help of another example. Now suppose if you're talking about demand for a good, this was income and wealth. Income and wealth would be multicollinear, there would be a linear relationship between income and wealth. So the chance of multicollinearity must have arisen in that case. So I'm taking a different example now. Demand equals to alpha naught plus beta 1 price plus beta 2 income. So now suppose we want to know the beta 1 is the partial slope coefficient, which means it would give us the impact of price on demand keeping other factors constant. Okay, now what we'll do is, in the initial case, we'll regress A naught plus B naught income plus U1. Solving this, after doing our regression analysis, we will have U1 hat with us. Now what we'll do is, we'll regress price on suppose C naught plus D naught income, U2 hat. So with the help of this, we'll get U2 hat. Now we'll regress U1 hat on suppose E naught U2 hat. We are regressing this on this. So basically the impact of income can be isolated in this case, because since demand is a function of income, we are regressing it, and then price is a function of income. Then with the help of this, we can know the partial impact of price. बेसिकली दोनों जगह इनकम को लिया ताकि सिर्फ प्राइस का इम्पैक्ट पता चल सके डिमांड पे क्या आ रहा है. ओके, now looking at the B part. Okay, the B part is saying, illustrate how would you remove heteroscedasticity in a model by making an assumption about variance of an error term. So if the variance of the error term, basically if sigma square equals to, if we are expecting sigma square to be sigma square xi square, so we can remove heteroscedasticity by So suppose if you have a model beta naught plus beta 1 x1 plus beta 2. Okay, suppose we have only one variable u1. Now yi equals to. Now we can transform the model in such a manner that we'll divide the model by xi, since it is xi square. So expected it would be yi upon xi equals to beta naught upon xi plus beta 1 plus ui by xi. So now if we'll take the variance of the error term, this would come out to be, okay, just wait a second. Okay, now we were here. If so, dividing the model by xi, this would cancel out ui upon xi. Now if we find the variance of the error term, summation ui xi square, so what we'll have is this would be sigma square xi square upon xi square. So this would cancel out, this would be sigma square only. So this is homoscedastic because there is no I in it. Similarly, if we know that it is of form this, then we will divide the model by root xi. I hope this is clear. So you can transform the model. In this model case, to the initial model, we'll divide this by root xi, and finally we will end up having a homoscedastic variance. Okay. Now moving on to the next part. Okay, this is the last question. The 7th is the last question. First thing, lin log and log lin models. So lin log model is of the form yi, it is linear on the dependent variable, and beta 1 plus beta 2 log xi plus ui. This is a lin log model. Now how do we interpret this? Suppose dyi equals to, this would be 0 plus beta 2 1 by x dxi. So beta 2 would be absolute change in y by relative change in x. So this is absolute change in y due to a relative change in x. Now talking about log lin models, they are of the form yt equals to y naught 1 plus r to the power t. If you will take log both sides, it would become log yt equals to log y naught plus t times log 1 plus r. So if we take this as beta 2, then and this as beta 1, we would have log yt equals to beta 1 plus beta 2t. In this case, beta 2 would give us the semi-elasticity. So if we multiply beta 2 by 100, it would give the growth rate or the instantaneous growth rate. Okay, now coming on to the second model, second part of the question, ANOVA and ENCOVA. So basically the basic difference is ENCOVA models takes into consideration the covariates as well. So we will have dummy variables. The interaction term would also be present with the slope. So this is a basic difference between ANOVA and ENCOVA. So they takes into consideration the control variables, the covariates as well. Now regression model through the origin and with the intercept term. So initially, suppose if you have a model yi equals to alpha naught plus beta 1 x1 plus beta 2 x2 plus u I. So this is a model with an intercept term present. In case if we have a model like this, so in this case there is no intercept term present. So some of the issues with in case when there is no intercept term present is, So the degrees of freedom would change. In this case it is, okay, in this case this is, the degrees of freedom are n minus k, but in this case it would be n minus k minus 1 if k is the explanatory number of explanatory variables. And one of the problems with the a model without an intercept is that summation ui hat is not equals to 0. But whereas if we talk about a model for which the intercept term is present, summation ui hat is always equals to 0. Okay, so this is one of the drawbacks of using a model without an intercept. And in case of a model without an intercept, we use raw r square, which is given as summation xi yi whole square upon summation xi square summation yi square. Whereas in case of a model with the intercept term present, r square is given as summation xi yi square. This has been taken in the deviation form, summation yi square. And this raw r square can be negative, whereas this r square is always greater than 0, greater than equal to. Okay, so this is possible when r square can be negative when we have a model without an intercept. Okay, and since r square, the formula of r square is different, we cannot compare the r square of the intercept model with the, so intercept 1 is the conventional model with the regression model which is through the origin. We cannot compare the r square of these two models. Okay, now coming to the C part, slope and interactive dummies, we have already done this when we were talking about structural change and all. Population regression function and sample regression function. So population regression function is for the whole population and sample is what we actually studies. The assumptions are made on the sample. So we know the multicollinearity problem is a sample phenomena. So we don't have, suppose this is the total population, we take this much data and we try to infer what the values of, suppose the model is yi equals to beta 1 plus beta 2 xi, what the values of beta 1 and beta 2 hat and beta 1 hat would be. We try to infer from this small data for the whole population. I hope this was clear and all the best for your exam. Thank you.